see if it works. And again, look at your domain restrictions. If you have no domain restrictions, every x you put in has to get a y. So this parabola has no domain restriction. You can even put it in your y equals. This denominator, no domain restriction, because this is an x squared plus 1. No domain restriction, so any you put in is good. This one fits right in. The angle, when it's 1, 2 pi, or what is this, as pi approaches 1, so 2 pi over 3, we have an angle. That works the sine curve. Continuous. Any angle you find is going to have a sine. So direct substitute it in. It just kind of gave you a little variety that you could look for limits on all different types of functions. Cancellations, these are your factoring. And again, some of them have this is where your domain is. Your domain is equal to 0. So whenever I say, what is it when it's 0? I can't plug a 0 in here. So this is when we factor. This one would work. This one would work. It has a limit. But the one at 0 approaches that limit. It approaches this. So we say it has a limit of 1. What its y value would be if I could actually fill the point in, remove that point. Something wrong, Jordan? You don't have this? Oh, no. Oh, okay. Sorry. Okay. Are we good with that one? How about this one? Good? Factor it, take out the common factor. That's the old point of discontinuity. That's our point of discontinuity. And when we found our point of discontinuity, we took what was factored and we plugged it into that one. And we got the y value. So if you do it graphically, and again, try them graphically, because graphically, they should approach the same point. Go to your table set it at 2, set the x at, what is this, 1, set it at 1, and put your table in 0.001. You'll see it approach the same number. It's got to approach the same number from the left side and the right side. And some numbers automatically have a limit. Kind of remembering the point of discontinuity? Kind of, sort of. I find that even though we do this during the year and we rename it for you, it's a good review because it brings you back to those things that we did with today. We'll do the review like of asymptotes that we did. So it kind of brings that back fresh in your mind because I think we did all that in the fall. Take out your common factor. Again, that's your point of discontinuity when x is 7. So if you try to do a direct substitution and you plug the 7 in, it would be undefined. So that kind of tells you, well, something else. Maybe I can factor it and cancel. They call it cancellation. We factor it and reduce it. If you're looking on your table, you'll clearly see a decimal. It'll approach the same decimal from both sides. Here's my x plus 1. So here's my domain restriction. All real numbers except for x is -1. Again, confirm it on your calculator. These guys, how did you do with the rationalization? Use its conjugate. You have perfect squares. So you multiply your first term, you multiply your last term. This is going to reduce. Slide this one over. Don't distribute it or you're just going to have to factor it back out. Your goal is to get rid of this guy. So leave it outside. These will reduce and your y will come out. This is fine. You can leave it just like that because now we can plug in a y of 0 and get a value out of that. And again, confirm it on your calculator. Okay. 19 was the same. Rationalization again. Are all my numbers different than yours? Yep. Sorry about that. So if I plugged in a -3, it would be undefined. So I'm going to have to get rid of that x plus 3. So I rationalize my numerator, and then you can see that this is going to come out. X plus 3 will come out. Slide it right over. And leave your rest of your function looking like that. That's absolutely fine. Your goal is to be able to plug in a negative 3 and find out what would that y be as it approaches that x from both sides. We call it a removable point. Today we'll look a little bit more at what's removable, what's not removable. That's considered a removable point. I can just fill it in, and then my pencil will go right through it and be continuous. Okay, this next one, complex fraction. So if I plugged in a 0 for x, I would have an undefined fraction. So your goal is to put everything over 1, find your common denominator, x times x plus 1, and reduce it down. Then substitute in your x of 0. Everybody okay with this one? No? So there's a number of ways to do it. I took the common denominator, and I usually don't. I usually do it this way. Your common denominator is just x plus 1. So multiply everybody by x plus 1. Just be careful of this negative sign. This is going to come out. Watch that. Keep that negative sign. Keep this in parentheses right now. And then this is your x times x plus 1. Distribute. Out comes your 1s. And you can take out the x, and you're left with a negative 1 over x plus 1. Use a common denominator. It works better. Questions? No questions? Okay, there's a little rationalization. Did you have these? Yes.
Let's get negative 1 for over, I know you got 9, but how'd you get the negative 1?
The negative 1, because when these canceled out, watch this negative sign. It distributes. Did you not get that negative x in there? Did you want to rationalize it again?
Oh, no, I just didn't distribute.
Oh, you didn't distribute. That's what I said. That's the tricky guy, this one right here. That negative sign. Watch that negative sign. So I'm going to multiply by 3 times 3 plus x. Maybe not. Okay, so this is coming out. So you're getting 3 minus, be careful of that negative sign. And this becomes 3x over 3 plus x. Distribute this guy. You can't cross those out. So out comes those. Now you can take an x out of here. Negative 1 over 3 times 3 plus x. Good? Just enough. This is nothing that you really haven't seen. You just haven't looked at it this way as we approach from both sides, finding a limit for the points that are not continuous. This is not continuous also, but there's no point that we could connect those two parts. We call this a jump discontinuity. It jumps from one place to the next. So there's no common point in between here that we could connect them. So the limit does not exist. It's a jump continuity. From the right, and we say it this way. This is how we write this, in case you see this. As x approaches 3 from the right, from the positives, okay, it's hitting a y1, and we can clearly, well, almost see that from there. From the left, from the negatives, it's approaching negative 1. they're not approaching the same number. So there's no limit. The limit does, and we just say the limit does not exist. It's called the jump discontinuity. Here's your piecewise, and this is good to review piecewise, because with piecewise, if you remember, we made tables for these guys, and this is where it's going to have a problem. This 2 is closed, this 2 is open. If they meet at the same point, then this is continuous. If they jump and they don't meet, and we can absolutely have a graph that goes here and then starts here, this has no limit. The limit does not exist, because this would be a jump. This is continuous. If you can fill it in and keep your pencil straight through it, it's continuous. And was that it? Did you have any questions on this? What was, when the degree is the degree is higher in the numerator. Okay, let me start again. The highest degree in the numerator is less than the highest degree in the denominator. We used to say this, y equals 0, right? So where is y equals 0? Where do I find y equals 0? The x-axis. So if this is my graph, what am I approaching? If my asymptote is y equals 0, as x goes on and on and on, what y value am I approaching? 0. So my limit is 0. It's the same rule, because your asymptote clearly takes care of your end behavior, says don't you come over this. Well, a horizontal one we can actually jump over, but then it comes back down. Even if we jump this, remember we had a couple of times we jumped over, but then it came back down and rode right alongside of it. So it still is y equals 0. When the highest degree in the numerator and the denominator are equal, so if you have a case like this, 2x squared over 3x squared, we said y equals 2/3. So now we just say it approaches 2/3. It rides right along that. It can't go over it. Okay, but it's going to come back up and ride right alongside of it. So now instead of saying y equals, we just say the limit is 2/3. And your last one, when the highest degree in the numerator is greater than the highest degree in the denominator, the limit does not exist, because we said there was no horizontal asymptote, right? And what happened when the degree in the numerator was 1 more than the degree in the denominator? What did we look for? If I have this, we said there's no horizontal asymptote, therefore there's no limit. If there's no horizontal asymptote, it does not exist. But what did we look for when we had 1 more of the numerator?
Was it a slant?
Yes, it was a slant asymptote. Very good. And if we had a horizontal asymptote, we could not have a slant, because it can't cut through that. Well, it can. Yeah, it can kind of, but they're a little different. So we had things like that. It's the exact same rules. We just call them for your calculus terms. Your calculus doesn't say y equals 0. It just says the limit approaches 0. In this case, it approaches 2/3. This one does not exist. So it's the same exact rules, which is kind of nice, because when you see that, it starts you thinking again, oh yes, I remember doing that. A couple of you picked up that it was horizontal asymptotes. Ryan got the slant asymptote. So it's a good time to help you review a little bit as well. So all we need to do with these guys is exactly test this. So when we have the degree in the numerator is less than the degree in the, say I would say it this way instead of the way this one's worded. When we say the degree in the numerator is less than the degree in the denominator, what's my asymptote? My y equals 0. So what's my limit? So let's change this as x approaches infinity. 0. That's it. That's the only difference. We're just throwing the limit in there. When the degree in the numerator is equal to the degree in the denominator, that's your second one. My asymptote was -2/3, so now I say this. The limit as x approaches infinity is what? -2/3. I just got rid of my y equals, that's all. I just said y is going to eventually be negative 2/3 if it could ever reach that. And the last one, oh, not the last one. When the degree in the numerator is greater than the degree in the denominator, that's your third one. We say there's no horizontal asymptote, so we say the limit as x approaches infinity does not exist. That's it. Same exact rules you knew before. And doesn't that make sense that a horizontal asymptote guides the end behavior, which tells us what value would you approach if you ever could touch it? Now this last guy, I put this last one here because you have to, I don't know if you remember back, you have to convert this to one term before you can check where your variables are. So if we convert this over x squared, I multiply numerator and denominator by x squared, and now I can say where is my piece. So my numerator and my denominator are the same. So what's my limit as x approaches infinity? Four over 1, so 4, right? Y is equal to 4, 4 over 1. And you can confirm them graphically if you want to as well. So we've seen these before. We know that they work. Did I give you the answer to that one? Or I didn't on that one. I did it on that one. Alright, so all you're going to do for this guy is kind of look over your rules. Because this has no bearing on connecting this here. I have to jump. This is a jump discontinuity if this point was not reachable, if this limit did not exist. But this limit right here at this point exists. If I fill this in, it has to be y equals 1. So here's your major difference. If I say, what is the value of your function at x is 2, then your answer is this y value up here. If we say, what is the limit as x approaches 2, where's that going? Where's that line converging at? On that little point right there at 1, right? It's converging right at 1. The limit does not exist here when f is 1. I could do the same thing here. What's the value of f of 1? What's the one filled in? 1, right? This guy's open, this guy's filled in. Is this a function, this part? Yes, because 1 is filled in, 1 is not. So we only have one value of y for every x. One value, even at the 0. Look at the 0. We have only one value, which makes this a function. This is a function right here. But here's the difference. If we say at f of 1, what is my value? It's 1. Do we have a limit as x approaches 1? As x approaches 1, do we have a y value that we can fill in? No. No y values. So the limit does not exist. That limit does not exist. And we call this, and we're going to see this in a minute, a jump discontinuity. You physically jump. Picture your pen just being right there. It's going to have to lift up and go up here. It's going to have to jump over this. Okay. What might be a little confusing is when we come from the sides. This is just an interior point. You're fine with this. When we're coming from the right and coming from the left. Oh, something happens here. One of these is a plus. Does this show up as a plus on yours? That's the plus. They both look like a minus to me, but that has to be a plus. So when you're coming from the right, from the positives, you're coming from the right. The limit exists. There's nothing coming from the left. When you're doing a negative, you're coming from the left. That sometimes is a little bit confusing. So just remember that negative means you're coming from the negatives. The positive means you're coming from the positives. Kind of think of it like that, not towards it, from it. A removable point, this is your point of discontinuity. This is your lovable point of discontinuity. the point that we could say, once we reduce your function, get rid of that domain restriction, if we can replace it, we plug it in and we find out what that y value would be. Or we put it in our calculator and we find out what that y value would be. So there's your point of discontinuity. We call it a removable point. The point may not make the function continuous. However, as the limit approaches 0 here, you can remove this point. So whatever value that is, 1, whatever. There's your jump, and this one we talked about earlier. There's your limits without the limit does not exist because it keeps on going up and up and up. That asymptote sits right in the middle of it. Okay. So, just kind of, I don't know if I have the worksheet. I don't know if I have the worksheet. Let me see. No, I don't think I have that one. Yep, I have the worksheet. All right. I think that's parts of it. That there's a piecewise here where you have the piecewise to this.
Are you pointing down because see how it's below?
Is it down there? Up it is. There it is, right?
Yeah.
Okay, thank you. I don't know what happened here. Okay, thank you. There it is. So this is your piecewise function. So again, if you're from -1 to 0, the -1 is going to be filled in, the 0 is going to be open. So the -1 is filled in, the 0 is open. It's a piece of a parabola. From 0 to 1, both of them are open, from 0 to 1. That's open. So it was a part of a line, from 0 to 1, piece of a line. At 1, we're filled in at 1, just one point. This point, this is the only point. Oh, now it's back. Okay. This point, again, this will make this continuous if we find the value of this. The limit as x approaches 1 is what? What would that y value be? What's this y value? 2. What's f of 1? 1. But for our limit, this does not help me in my limit. That would make it a jump. I want to know what value does this approach from left and right that I could just fill in and remove that point. That's a removable point. If I could put my pencil and color that in, I'd be able to continue right over it. So what makes this continuous? That's what my limit does. Okay? If I say this, what is my limit as x approaches 2? What value of y could I put in there to make this continuous? 0. Good. What is my limit as x approaches 0? The limit does not exist. Good. Because what is that? It's a jump. If I throw my pen around here and I say, okay, can I fill this in and continue? No, I can't. I got to pick my pen up and go up to here. That limit does not exist. So do we kind of see what I like this diagram. They're a little bit redundant here and there, things that they're asking, but I do like this diagram. How about at 3? Which side am I approaching from? I'm approaching from the positives or the negatives when I come from here? From the left or from the right? From the left for 3. If I'm approaching from the left-hand side, right? What would my limit be for this guy? What's my y value? 0. From the right-hand side, does not exist. There's no right-hand side here. Okay. So again, just be careful of where the limits exist. This was okay, this worksheet, but it's kind of like redundant. It asks the same thing over and over. I do like this part down here. Again, if I label these points, which point is removable? Which point could I fill in and make my line continue? A or B? B. So as my limit, what is my limit as x approaches 2? What value would you put in there? 1. What value would you put in there to make this continuous? 1. Not the same as this. What is my value at 2? Then it's 2. But my limit as x approaches 2, I would have to color in, fill in that little hole, and put it when y is 1. What's this guy called? A jump. This is point A. The limit does not exist. I have to physically pick my pencil up, jump over. The limit does not exist. Okay? And these down here were pretty good. I like these guys too. Again, let's label these. Okay? Which point is removable? A, B, well, not B. B is filled in. A or C, which point is removable? C. So how would I write that? The limit as x approaches what value? 2 is equal to 1. That'd be it. What value can I circle this in so that now this piece can be continuous? This is continuous from -1, all the way to here at 1. Then I stop. This is not continuous here. I'm not being able to come down here. It jumps here. This limit does not exist. So I would say, what is the limit as x approaches 1? As x approaches 1. That limit does not exist. This guy right here. There's nothing I could fill in to make that connect so that I wouldn't have to pick my pencil up. Okay? Is it making sense? Kind of like things we did. Point of discontinuity versus asymptotes. We did asymptotes. We didn't do jumps, but you can kind of see the jump part. I don't know what's on the bottom part. This is a good one to do. So if you have this, this one is supposed to have an equal sign under it. Does yours have an equal sign? The second one? This one's supposed to have an equal sign under it. So if this was a piecewise function, and I wanted to know for what value of A would make this thing continuous. I've got a piece over here that's a part of a parabola, and I've got a piece over here that looks like it's a part of a line somewhere. What value of A could I plug in to make this continuous? What does it mean to you first that has to happen? Let's take this guy. Anything less than 3, so like 0, so 3, 2. All the way down. This guy's going to be open, right? This guy's going to start here and be closed. For this to be continuous, what has to happen? What has to be my values? Or what do they have to look like? My value at 3 in both equations has to be the same or different? The same. So they have to be the same to make it continuous? One has to be opened at it, one has to be closed at it. It's just another way to say, is this going to connect? Is it going to be continuous? Am I going to be able to put my pencil down and not pick it up? If they meet at 2 different places, I have a jump discontinuity. So I want to know that this value has to be equal to this value. So how can I do that? So what if I plug in 3 for this? Let's see what 3 gives me here. 3 squared is 9, minus 1 is what? I need this one and this one to be exactly the same. I need it to be continuous, no gaps. So when I make 3, 8, this guy's going to say 3, 8, open. This guy's going to say 3, 8, closed. So therefore, what does this have to equal? 8. So now this has to equal 8. Do you see it? Being continuous and being a jump? If it's a jump, I don't care what A is. It can be anything else. It doesn't have to make me meet. But for me to meet in one point, that has to be the same. Okay. I did have another little worksheet I wanted you to look at, but maybe we can look at that tomorrow. Concentrate on what you have there. The last test, remind me tomorrow, I'll get them out. Yeah.
All right, so I wasn't here.